In this section, I want to talk about probability distribution functions and cumulative distribution functions, and I want to explore the relationship between them. Is something bugging you? Well, there should be. If we have a continuous variable, what's the probability that an observation has exactly the value x? Now, I want to approach this question by taking a step back. So we're going to look at it rather obliquely, as it were. First of all, let's actually, rather than consider the continuous case, think for a moment about the discrete case. Consider an experiment with discrete outcomes. For example, one roll of an unbiased six-sided die. Clearly, only one of the 6 outcomes is possible. The probability mass function, which is the analogue of the probability distribution function for discrete variables, assigns equal and positive mass to all possible outcomes. Of course, 0 is not possible, but 1, 2, 3, 4, 5, and 6 are all equally probable. Now, in this case, the height of the line above the x-axis directly gives you the probability of the outcome. Now consider the probability density function of a continuous variable. This one is normally distributed with mean of 0 and variance of 1, and if it has a variance of 1, the standard deviation is also 1. The height of the curve above any particular value on the x-axis does not give you the probability of obtaining that value. In fact, the probability of obtaining any particular value is 0. Recall that in the probability density function, probability or proportion is equal to an area under the curve. Choose 2 points on the x-axis close to each other and connect them to the curve with perpendiculars. You could move them closer and closer and closer without them ever meeting, because by definition a mathematical line has 0 width, and therefore the area between them can be infinitely small. So what then does the curve represent? Now at this point we have to bring in the cumulative distribution function, or CDF. This is often denoted capital Fx. Again, let's look at an example for a normally distributed variable with mean of 0 and variance of 1. This cumulative distribution function corresponds to the figure that I showed you on the last slide where we plotted the PDF. What are we doing with the cumulative distribution function? We're accumulating the observations between negative infinity and positive infinity. The y-axis gives the probability or proportion below a given score on the x-axis. Now this implies that when the cumulative distribution function is relatively flat, that there's not much of the distribution there to accumulate, and you can see that it's relatively flat at both the left-hand side and the right-hand side of the figure. In the middle, however, where the gradient is steep, things are changing rather fast over small intervals. So there must be quite a lot of observations in that region. Let's zoom in on the cumulative distribution function. What I want to do is to zoom into this central section which is located around the mean of x. What that means essentially is located around the 0 point in x. In the first graph on the left-hand side, we've plotted the CDF between -3 and +3. You can see that for these values, it's a sort of S-shaped curve. If we then narrow the focus down a little bit and zoom in on the region -2 to +2, we see it's still somewhat S-shaped. If we go down to the bottom, we're zooming in to the portion between -1 and 1, and you can see that it's beginning to look an awful lot more linear, an awful lot more like a straight line. Okay, on this slide, let's focus in even more closely to the region around the mean of 0. Let's focus on the area between the values of x -0.01 and 0.01. So we're getting reasonably close. We're examining a region which is reasonably close to the mean. Project up 2 perpendicular lines and then project them over to the y-axis. We can then read off the corresponding values on the y-axis. You might remember from high school algebra or mathematics generally how to calculate the gradient of a line. It's the rise over the run. The rise in this case, we take the values from the y-axis, approximately 0.504 minus approximately 0.496. That gives us a value of roughly 0.008. So the gradient, the rise over the run, is going to be 0.008 divided by 0.02. And that gives us a value of roughly 0.4. This value might ring a bell. You might recall from previous slides where we looked at the probability density function for a standard normal variable, one with a mean of 0 and a standard deviation of 1. You might recall that it reaches a maximum y value of roughly 0.399, around about the mean. Our value of 0.4 closely corresponds to this. So, what is the probability density function then? A probability density function is actually just a plot of the first derivative of the cumulative distribution function with respect to x, and it reaches a maximum when x equals the mean. So, the probability density function for a continuous variable and the cumulative distribution function are really just two sides of the same coin. The probability density function, small f of x, is the derivative of the cumulative distribution function with respect to x. And the cumulative distribution function, big F of x, basically integrates the probability density function with respect to x between -infinity and whatever value of x you're interested in.